Our lesson today is on thin convex lenses, and you can recognize a convex lens by the fact that it's wider in the middle than it is on the ends. And when we get done with thin convex lenses, we'll do a concave lens, which will be the opposite. Let's identify first of all some characteristics of a convex lens. Well, there should be a focal point on either side, same distance. And you're going to find that light rays are refracted through these focal points. Let's label that F. And if we put an object, let's say just an arrow here, and I'll just label O. O is going to be the object distance. It'll be the distance the object is from the lens. And then on this side here, there will be an image form. Let's just place it right here. We don't know where it would be. Let's just place it there. And we'll label this I. And that's going to be the distance that the image is from the lens. Now let's get our sign conventions figured out here. When the object is in front of the lens, we have to pick what side we want that to be. That's going to be a positive object distance. If our object is on the same side as our image, then that'll be a negative object distance. If the image is on this side of the lens, opposite of the object, that's going to be positive. But if the image is formed on the same side of the object, the image distance will be negative. So we see that anytime that object and image are on the same side, one of them is going to be negative. And it depends on what you're looking at, how you can figure out what that is. So we then use the fundamental lens equation. 1 over the focal length is equal to 1 over the image length plus 1 over the object length. And it turns out that when your object is on the left side or farther away from the lens on the focal point, you will get a positive image distance. And this is going to be for a real inverted image. When we put our object inside the focal point, you're going to get a negative image distance, and you're going to get a virtual, upright image. A real image is one that can be projected to a screen and everyone can see the same image. A virtual image is one that is only produced inside the viewer's mind, and then it becomes upright and it is not real. So this one's comprised of actual light rays that everyone can see, and this one's inside the mind. Now what about magnification? Magnification is equal to minus I divided by O. So it's the minus of the image distance divided by the object distance. And the magnification means how many times the image is than the actual object. Looking at this right here, it looks like this one's about half the size of this. So for our brief setup here, the magnification is going to be equal to a 0.5. And it'll turn out negative because this guy's upside down. Now, we would calculate that actually using this equation. So we're just setting up a possible answer here, and we've done no calculations on it. But we just wanted to get a meaning behind what everything is. Our first step in this is going to be looking at light ray tracing diagrams. And then we're going to look at a combination of lenses and actually apply these formulas and show you how they work. After we get done with that, we'll look carefully at a convex lens, or a concave lens. Okay, let's get started. Light ray tracing right now. Okay, let's say I've got an arrow, and this arrow is glowing, so the light is coming off of it, or light is reflecting off of it. How do we do a light ray tracing diagram? Well, there's a couple ways. I like to use a 2-ray method. The first ray is parallel to the lens, and then is refracted through the focal point and ends up there. The second ray, again coming from the same tip, goes straight through the center of the lens and comes out the other side. Where the 2 rays intersect, that's where the tip of the arrow is going to be. Now you can imagine an infinite number of rays we would trace, and we would be tracing those and eventually make our image like this. So we just do 2 rays like this. Okay, so this is for an object placed outside the focal point of a convex lens. What about placed inside? Well, here we go. We've got our arrow here. So what we do then is we take the first one up at an angle, and then it goes parallel. Then this one goes parallel and gets refracted through the focal point. We notice that they diverge. These converge to a point, these diverge. Okay, and then, well, where is the image actually seen? Well, imagine placing an eye on this side, and I'll just draw a quick little diagram. This is for someone's eye looking in this way. The eye is going to think a light ray is coming here, and one is coming here. And what's going to happen is we're going to trace those back, and the eye is going to think both of them came from this spot here. And again, if we did an infinite number of those, we'll be actually tracing, okay, our arrow like this. Okay, now this is an optical illusion. So this one is our virtual upright, okay, and this one is our real inverted. Please notice how image distance here is equal to a positive. And over here, since the image is formed on the same side of the object, our image distance here is going to be negative. When we apply the equation m, magnification, equals minus I divided by O, this one will give us a negative magnification. And the negative means the arrow is upside down. But when we do this one, we'll take a minus of a minus, and our magnification will be positive, therefore meaning the arrow is right side up. This one is comprised of actual light. We can project that onto a screen and see it. But this one, we have to look through the lens in order to see the image on the other side. So this is our virtual. It'll occur in someone's mind, whereas this one here will occur, okay, for all to see. And that's how we do ray tracing diagrams. In our next video, we'll look at combination of lenses, and we'll look at the concave lens.